Hello and welcome. In this video, we will explore constant velocity problems using vectors, a key topic in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to model the motion of an object moving at a constant velocity using a vector equation, calculate its speed, and solve complex problems involving position, time, and direction. Let's begin by understanding the fundamental principles. When an object moves with a constant velocity, it travels in a straight line. We can describe its position at any time using a vector equation. The general form of this equation is r equals a plus t times b. Let's break down what each part of this equation represents. First, r is the position vector of the object at any given time. T, it tells us the object's location in space. Next, a is the initial position vector. This is the object's starting point when time, t, is 0. Then we have b, which is the velocity vector. This vector defines both the direction of motion and the speed of the object. Its magnitude, or length, is the speed. Finally, t is the parameter representing time. It's a scalar value that scales the velocity vector. So the equation r equals a plus tb means that to find the object's position at time t, you start at its initial position, a, and add t times its velocity vector, b. This addition moves the object along a straight line. Visually, it looks like this. From the origin, the vector, a, takes us to the starting point. The vector, b, shows the direction of travel. At time t, we add t times b to a to get the final position vector, r. A crucial distinction to remember is between velocity and speed. Velocity is a vector. It has both magnitude and direction. Speed is a scalar. It only has magnitude. The speed of the object is simply the magnitude of its velocity vector, which we write as the absolute value of b. Now that we have the framework, let's work through an example. Let's consider our first example. An object's path is described by the vector equation. The vector x, y, equals the vector 1, 9, plus t times the vector 3, negative 4. We need to find several things about this object's motion. First, its initial position. Second, we'll plot its path. Third, we'll find its velocity vector. Fourth, its speed. And finally, we'll find a new velocity vector if its speed changes. Let's start with part A, the initial position. The initial position occurs at time t equals 0. Substituting t equals 0 into our equation, the t times b term becomes the 0 vector. This leaves us with the initial position vector, which is 1, 9. So the object starts at the point 1, 9. Now for part B, plotting the path. To plot the path, we'll find the position at a few different times. We already have t equals 0, which is 1, 9. For t equals 1, we get the vector 1, 9 plus 3, negative 4, which is 4, 5. So at 1 second, the object is at 4, 5. For t equals 2, we have 1, 9, plus 2 times 3, negative 4, which simplifies to 7, 1. At 2 seconds, it's at 7, 1. And for t equals 3, we get 1, 9 plus 3 times 3, negative 4, which is 10, negative 3. At 3 seconds, it's at 10 minus 3. If we plot these 4 points on a graph and connect them, we can see the straight line path of the object. This visual confirms our understanding of constant velocity motion. Next, part C, the velocity vector. From our general equation r equals a plus tb, we can see that the velocity vector, b, is the vector that is multiplied by t. In this case, the velocity vector is 3, negative 4. Now for part D, the speed. The speed is the magnitude of the velocity vector. We calculate the magnitude of 3, negative 4 using the Pythagorean theorem. That's the square root of 3 squared plus negative 4 squared, which is the square root of 9 plus 16, or the square root of 25. The speed is 5 meters per second. Finally, part E, a new velocity vector. The problem states the object continues in the same direction, but increases its speed to 30 meters per second. The direction is given by our original velocity vector, 3, negative 4. The magnitude of this vector is 5. We need a new vector with the same direction, but a magnitude of 30. To do this, we find a unit vector in the direction of b by dividing b by its magnitude. Then, we multiply this unit vector by the new desired speed, 30. This gives us 30 over 5 times the vector 3, negative 4, which simplifies to 6 times 3, negative 4. The new velocity vector is 18, negative 24. In this example, we've successfully applied the vector equation of a line to describe motion, calculated speed, and manipulated velocity vectors. This covers our first two learning objectives. Now, let's extend these concepts to 3 dimensions. The principles remain the same, but we'll be working with 3D vectors. Consider a mermaid initially at the point 15, 8, minus 1. Her velocity vector is 3i minus 5j minus 9 over 2k in meters per second. We need to find her position after t seconds, her speed, and the time when she reaches a depth of 28 meters. Let's find her position vector at time t. We use the formula r equals a plus tb. The initial position vector a is 15, 8, negative 1. The velocity vector b is 3, negative 5, negative 9 over 2. Combining these, we get the position vector r of t. This vector r of t gives us the mermaid's x, y, and z coordinates at any time t. So after t seconds, the mermaid is at the point with coordinates 15 plus 3t, 8 minus 5t, and negative 1 minus 9 over 2t. Next, let's find her speed. The speed is the magnitude of the velocity vector. We calculate the magnitude of 3, negative 5, negative 9 over 2. This is the square root of 3 squared plus negative 5 squared plus negative 9 over 2 squared. This simplifies to the square root of 9 plus 25 plus 81 over 4, which is the square root of 54.25. The speed is approximately 7.37 meters per second. Finally, let's find the time when she reaches a depth of 28 meters. In this problem, depth is represented by the z-coordinate. We need to be careful with the sign. If the initial depth is minus 1, then a depth of 28 meters means the z-coordinate is minus 28. We set the z-component of our position vector, negative 1 minus 9, over 2t, equal to negative 28. Solving this equation for t, we add 1 to both sides to get negative 9 over 2t equals negative 27. Multiplying by negative 2 over 9, we find that t equals 6. So the mermaid reaches a depth of 28 meters after 6 seconds. This example demonstrates how to apply vector equations to solve problems in 3 dimensions, including interpreting coordinates as physical quantities like depth. This fulfills our third learning objective. Let's tackle a more complex problem, one that involves the relative motion of 2 objects. This is a common type of question in IB exams. We have 2 yachts, A and B. Their positions are given by these 2 vector equations. Yacht A's position is 4 plus t, 5 minus 2t. Yacht B's position is 1 plus 2t, negative 8 plus t. The time t is in hours, and distances are in kilometers. We need to find their initial positions, velocity vectors, and speeds. Then, we'll show that their paths are at right angles to each other. First, let's find the initial positions and velocity vectors. For yacht A, the initial position is the constant vector, 4, 5, and the velocity vector is the vector multiplied by t, which is 1, negative 2. For yacht B, the initial position is 1, negative 8, and the velocity vector is 2, 1. Next, let's find their speeds. The speed of yacht A is the magnitude of its velocity vector, 1, negative 2. This is the square root of 1 squared plus negative 2 squared, which is the square root of 5 kilometers per hour. The speed of yacht B is the magnitude of its velocity vector, 2, 1. This is the square root of 2 squared plus 1 squared, which is also the square root of 5 kilometers per hour. Both yachts are moving at the same constant speed. Now for the most interesting part, showing their paths are at right angles. The paths of the yachts are determined by their velocity vectors. If the paths are at right angles, the velocity vectors must be orthogonal. We can test for orthogonality using the dot product. If the dot product of 2 non-zero vectors is 0, they are orthogonal. Let's calculate the dot product of b underscore a and b underscore b. We multiply the corresponding components and add them. That's 1 times 2 plus negative 2 times 1. This gives us 2 minus 2, which equals 0. Since the dot product is 0, the velocity vectors are orthogonal, and therefore, the paths of the two yachts are at right angles to each other. This example shows how the dot product is a powerful tool for analyzing the geometric relationship between vector paths. We've now seen how to compare the motion of two objects, which is a key skill for IB problems. Let's tackle another multi-part problem, this time involving a torpedo and a submarine. This problem introduces the concept of a time delay. At 1:34 p.m., submarine P fires a torpedo from the point -5, 4 with velocity vector 3, -1. A minute later, submarine Q fires a torpedo from 15, 7 with velocity vector -4, -3. Distances are in kilometers, and time is in minutes. We need to find the position of P's torpedo, its speed, the position of Q's torpedo, the angle between their paths, and finally, the time, A, and the time of impact if Q's torpedo hits P's. Let's start with P's torpedo. Its initial position is -5, 4, and its velocity is 3, -1. So, its position vector at time t is -5 plus 3t, 4 minus t. The speed of P's torpedo is the magnitude of its velocity vector. That's the square root of 3 squared plus -1 squared, which is the square root of 10 kilometers per minute. Now for Q's torpedo. This is where the time delay comes in. Q fires, A, minutes after P. So if P's torpedo has been traveling for t minutes, Q's torpedo has only been traveling for t minus a minutes. We replace t in the standard equation with t minus a. This gives us the position vector for Q's torpedo. Next, the angle between their paths. The angle between the paths is the angle between their velocity vectors. We can find this using the dot product formula. The cosine of the angle theta equals the dot product of the vectors divided by the product of their magnitudes. The dot product of B underscore P and B underscore Q is -9. The magnitude of B underscore P is the square root of 10, and the magnitude of B underscore Q is 5. So the cosine of theta is -9/5 times the square root of 10. Taking the inverse cosine, we find the angle is approximately 124.7 degrees. Finally, the time of impact. If Q's torpedo hits P's, their position vectors must be equal at some time t. We set r underscore P of t equal to r underscore Q of t. This gives us two equations, one for the x components and one for the y components. Solving the y equation first, we find that t equals 3a plus 3. Substituting this into the x equation, we can solve for a, which is 2. This means Q fired its torpedo 2 minutes after P. Now we find the time of impact by substituting a equals 3/17 back into our equation for t. This gives us t equals 60/17 minutes. The explosion occurs 60/17 minutes after 1:34 p.m. This problem is a great example of how to handle time delays and solve systems of equations to find collision points. It combines several of the concepts we've covered. Let's conclude with one more example, this time in 3 dimensions, involving a cable car. This problem will focus on finding the angle of travel. A cable car leaves from the point 10, 3, 0. It moves in the direction of the vector 2i minus 2j plus k at a speed of 4.5 meters per second. We need to find its velocity vector, its position after 30 seconds, the length of the ride to a destination with an x-coordinate of 550, and the angle at which it travels to the horizontal. First, the velocity vector. We are given the direction vector 2, -2, 1, and the speed 4.5. The magnitude of the direction vector is the square root of 2 squared plus -2 squared plus 1 squared, which is 3. To get the velocity vector, we scale the direction vector by the ratio of the desired speed to the current magnitude. This gives us 4.5/3 times the vector 2, -2, 1, which simplifies to 1.5 times the vector, resulting in the velocity vector 3, -3, 1.5. Now, the position after 30 seconds. We use r equals a plus t, b. The initial position, a, is 10, 3, 0. The time, t, is 30. And we just found the velocity vector, b. Substituting these values, we get the position vector, 100, -87, 45. So, after 30 seconds, the cable car is at the point 100 minus 87.45. Next, the length of the ride. We are told the destination has an x-coordinate of 550. We set the x component of our position vector, 10 plus 3t, equal to 550. Solving for t, we find that t equals 180 seconds. The length of the ride is the total distance traveled, which is speed times time. That's 4.5 meters per second times 180 seconds, which equals 810 meters. Finally, the angle to the horizontal. The angle the cable car travels to the horizontal is the angle between its velocity vector and a horizontal vector. A simple horizontal vector is the I vector, 1, 0, 0. We use the dot product formula again. The dot product of the velocity vector and the I vector is 3. The magnitude of the velocity vector is 4.5. The magnitude of the I vector is 1, so the cosine of the angle is 3 over 4.5, or 2 over 3. The angle is the inverse cosine of 2 over 3, which is approximately 48.2 degrees. This example shows how to construct a velocity vector from a direction and speed, and how to use the dot product to find angles in three-dimensional space. This is a sophisticated application of vector algebra. We have now covered the core concepts of constant velocity problems using vectors. You should be able to model motion, calculate speed, and solve problems involving position, time, and direction. To solidify your understanding, here are 5 practice questions in the style of IB assessments. Pause the video, work through them, and then resume to see the fully worked solutions. Here are the questions. Question 1 is a 2D problem. Question 2 is a 3D problem. Question 3 involves finding a velocity vector from a direction and speed. Question 4 is a collision problem. And question 5 asks for the angle of travel. Take your time to solve these. When you're ready, let's look at the solutions. Welcome back. Let's go through the solutions to the practice questions. For question 1, the initial position is found by setting t equals 0, which gives 2i plus 5j. The velocity vector is the vector multiplied by t, which is 3i minus 4j. The speed is the magnitude of this vector, which is the square root of 3 squared plus negative 4 squared, giving 5. For question 2, the position after 5 seconds is the initial position plus 5 times the velocity vector. This gives 1 plus 20, 2 minus 5, 3 plus 10, which is the point 21, negative 3, 13. The speed is the magnitude of the velocity vector, which is the square root of 4 squared plus negative 1 squared plus 2 squared, giving the square root of 21. For question 3, the direction vector is 3, negative 4, with a magnitude of 5. The desired speed is 20. We scale the direction vector by 20 over 5, which is 4. So the velocity vector is 4 times 3, negative 4, which is 12, negative 16. For question 4, we set the position vectors of A and B equal to each other. This gives us 2 equations. Solving the first equation for t gives t equals 10. Substituting this into the second equation, we get 10 equals 20, which is false. Since the equations are inconsistent, the particles do not collide. For question 5, we find the angle between the velocity vector and a horizontal vector, like the I vector. The dot product is 100. The magnitude of the velocity vector is the square root of 12,600. The cosine of the angle is 100 over the square root of 12,600, which is approximately 0.89. The angle is the inverse cosine of this value, which is about 27.1 degrees. I hope this video has provided a clear and rigorous explanation of constant velocity problems using vectors, as required for the IBAAHL curriculum. Keep practicing these types of problems to build your confidence and mastery. Thank you for watching.